everyone. In this lesson, we're going to look at how to apply and convert with scientific notation in context. So the whole purpose of scientific notation is to be able to write numbers expressed between 1 and 10 multiplied by a power of 10. It's for really large and really small numbers. And the key is there, it's between 1 and 10. So in other words, when we write scientific notation, we can't use the number 10 as the first number. So what I mean by that is, if you take this really large number here, which was the total spending in the 2020 federal budget, it's basically $6.5 trillion. If I was to write this in scientific notation, the first thing I'm going to do is find the decimal, and then I'm going to move back until I get to a number that's between 1 and 10. So if I move the decimal back 3, 6, 9, 10, 11 spaces, it takes me to the number 65, and that's not between 1 and 10. So I have to move it one more time, and now I have 6.5, and I just moved 12 places to the left. So that number is 6.5 times 10 to the 12th. Here you have the diameter of a hydrogen nucleus, and it's basically 0 meters. If I wanted to express that in scientific notation, I need to, again, find the decimal, but this time I'm moving to the right, and I would have to move 3, 6, 9, 12, 15 places in order to be between 1 and 10. So another way of writing this is 1 times 10 to the negative 15th power, since I'm moving to the right. Here's a couple for you to try, and there's some clues there and reminders about what tera and giga means. So you can try those on your own. One of the things we're looking at in this course is quantitative reasoning, and one of the skills we looked at was estimation. So one of the things we need to do is put that into perspective. Like, have you ever really thought about how high 1,000 feet is, or any large distance or length? So if you think about it, how would we put that in perspective or in terms that we are familiar with? Well, you figure like each story in a tall building is about 100 feet tall, is about 10 feet tall, right? And that's floor to ceiling. So you figure 1,000 feet is approximately 1,000 divided by 10, or a 100-story building. So think of the Empire State Building, right? That's about 100 floors. So that would be about 1,000 feet tall. Okay, so that puts it into perspective now when you're thinking in terms of that. We have this term order of magnitude, and you're going to see this a little bit in this section. So it's an estimate which specifies only a broad range of values. And we'll look at some examples here. Usually within 1 or 2 powers of 10. Such as the 10,000s or the millions, okay, for example. Okay, let's take a look at an example. So we need to make an order of magnitude estimate of the total annual spending on ice cream in the United States. Okay, so how would I figure that out? Take a second and think about that. Well, the first thing I know I would need to figure out is the amount each person spends annually on ice cream, right? And then I would need to know the total population if I'm looking for the total annual spending in the United States, okay? So I need to know the amount each person spends annually on ice cream. And I also need to know the total population. And then once I have that, I would just multiply the two together, right? Because I would know how much each person spends and then times the number of people in the United States. Well, how do we know how much each person spends annually on ice cream? Okay, so how would I figure that out? Well, we would have to make some estimations. So let's think about this. Total annual spending, let's talk about that. How would I figure out total annual spending? Well, I need to know the population, of course. I would need to know about how much ice cream each person is spending, or is eating. So each person, the amount they're eating, we would consider that like the serving size. And some people might have different serving sizes than others. So again, this is like a ballpark figure. And I would also need to know the price per serving. So total annual spending is going to equal the servings per person per year the price per serving and then the population. And once I know that, I could multiply them together and get the total annual spending. Okay, so let's think about this. I know I like ice cream, and I'm going to say that the average person maybe has at least one serving of ice cream each week. Okay, now what is a serving? Is it a scoop? If you go to Wendy's and you get a Frosty, does that count as a serving? So there's a lot of different ways we could define serving, right? So we'll just assume it's maybe like a scoop and maybe just a little bit more. That would be considered a serving. Okay, so, or maybe like one visit to the ice cream shop or, wherever you go to get ice cream, or you're at home and you put a scoop of ice cream in a bowl for yourself. So we'll say that there's 52 weeks in a year, so maybe that's about 50 servings per year. And that takes care of the people that maybe have more than one serving a week or maybe have less than one serving a week. I think 50 is a pretty fair estimate for that. So 50 servings, and then actually let's write this in terms of unit analysis. So 50 servings, and then it's per person per year, right? So 50 servings per person per year. How much would it be a serving? Maybe $1. So $1 for every serving. Now again, that would depend on your location, right? Some places might be a little bit more than others. And then how many people in the United States? So we can look that up, but it's about 300 million. Okay, people. Okay. So I know that servings are going to cancel. I know that people are going to cancel, and I'm going to be left with how much money per year. Okay. So all I need to do now is just multiply 50 times 1 times 300 million, which, by the way, you can express 300 million as scientific notation if you wanted. It would be 3 times 10 to the 8th power, because here's your decimal, and we're just going to take that and move it 1, 2, 3, 4, 5, 6, 7, 8 places to the left. Okay, so that's another way you could express that. But when you multiply 50 times 1 times 3 times 10 to the 8th, or 50 times 1 times 300 million, you get about 1.5 times 10 to the 10th dollars per year. So what is that? So here's my decimal point. I'm going to move that 10 places to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and fill in zeros. So that's going to be about $15 billion on ice cream. All right. I'm going to give everyone a chance to take a look at, so it would be $15 billion for the ice cream. Okay. I'm going to give everyone a chance here to pause and answer the following questions. Again, you're using estimation to make comparisons, and you want to think about, the conclusion that you come to here. Okay. Another thing we want to look at is perspective through comparisons. So to be able to think about maybe how big or small something is compared to something else. So let's say I give you this question: how big is $100 billion? Okay, I want you to really think about that. You could win $100 billion, you could earn $100 billion, but think about how big is that? How do you even think about that? So one way to look at it is maybe how long would it take you to count $100 billion in $1 bills? Okay, so how long would it take you to count $100 billion in $1 bills? So how would we figure that out? Well, you figure maybe it would take, let's see, if you counted $1 a second, right? Let's just assume that. It would take us 100 billion seconds. So let's start there. And 100 billion, if we were to write that out, right, that would look like this. Okay, that's 100 billion. So if I wanted to write that as in scientific notation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 1 times 10 to the 11th, right? Or just 10 to the 11th, but we can put the 1. Seconds. Okay, that's how long it's going to take you. But how do you even picture that? Like, what's 100 billion seconds? Well, we're going to do some unit analysis here. We're going to convert. So I need to turn this into something that I can think about, right? Maybe I want to turn it into like years, because you're not going to be able to count $100 billion in like a day. There's not 100 billion seconds in a day. So I'm going to convert now. So what do I know about seconds? Well, I know that there's 60 minutes in a second, or 60 seconds in a minute, So I'm going to have to put the 1 minute on top and the 60 seconds in the denominator so that the seconds will cancel. And then what do I know about minutes? Well, I know that there's 60 minutes in 1 hour. And what do I know about hours? Well, I know that there's 24 hours in 1 day. And what do I know about days? Well, I know that there's 365 days, okay, assuming it's non-leap year, and 1 in 1 year. So now my seconds cancel, my minutes cancel, my years, my hours cancel, my days cancel. And I'm just going to go straight across and multiply. So remember, 10 to the 11th is 100 billion. So in the numerator, you have 100 billion. Okay, so let's pull up a calculator. You've got 100 billion. So that's 100 and then 9 zeros, which you can also write as 10 to the 11th. So if you prefer to do that, you can clear that, right? And just do 10 to the 11th. Okay, and then what I'm going to do is I'm going to divide by all the denominators, right? The product of the denominators. So it's 60 times 24 times 365. And I end up with 3170.98, which is really 3,171 years. That's how long it would take you to count $100 billion. So now when you think about how big $100 billion is, right? When you think about how long it would take you, when you compare it to years and the length of time, it really makes you realize how big that number is. So perspective through comparisons is useful when you're dealing with units that are relatively unfamiliar or really large or really small. Here we have a table which can help you when you're trying to determine units that are maybe not familiar to you. So you can see things like the energy produced or released by metabolism for one average candy bar, or the energy released by, after 1 hour of running for an adult, and so on. So those are things that maybe, you're not familiar with, but with that table, you can figure it out. So in this example, we're going to compare the U.S. population to the world population and the U.S. energy consumption to the world energy consumption. So in other words, like what percentage of the world population is the U.S. and also what percent of the energy consumption do we actually use? And then what does this tell you about energy usage by Americans? All right, so to figure that out, right, to compare them, I'm going to create a fraction. I need to know the world population. And the world population is of order 8 billion. Okay, which we can write as 8 times 10 to the 9th because it's an 8 with 9 zeros. And the US population is about 300 million. Which we can write as 3 times 10 to the 8th power. So now I'm going to compare. I'm going to take part over whole. I've got the US population over the world population. So I know in the numerator I've got 3 times 10 to the 8th. And in the denominator I've got 8 times 10 to the 9th. Okay, so here I'm going to pull that 3 and 8 away from the 10 to the 8th and the 10 to the 9th. And since we're multiplying, we can do that. And you'll remember from before, anytime we divide like bases, we subtract the exponents, the power. So 8 minus 9 gives me -1. So it's 3/8 times 10 to the negative first. 3/8, if you divide 3 by 8, you get 0.375 times 10 to the negative first. And let's change that to a percentage, right? So we know what percentage of the world population is the US population. So if I was to write 0.375 times 10 to the negative first, I'll move back one place. That's what that -1 tells me. So really it's just 0.0375. And as a percent, I would multiply that by 100 or move the decimal 2 places to the right, which would give me 3.75%. So that's what percentage of the world population is the US population. It's roughly 4% of the world's population. Okay, that's what the US population is. Now, if we're looking at energy usage, again, we're going to compare. We're going to do the US energy usage, and we're going to compare that to the world energy usage. And we're going to get that from the table. Okay, so let me shrink this so I have more room here to write. All right. So if I look at my table, it tells me that the US energy usage is 1.0 times 10 to the 20th, and the world annual energy usage is 6.3 times 10 to the 20th. And the 10 to the 20th are going to cancel, right? Because 10 to the 20th divided by 10 to the 20th is just 1. And I've got 1 divided by 6.3. And if you type in our calculator, what is 1 divided by 6.3? It's like 0.16, which we know is 16%. So what does this tell me? It tells me that the US uses about 16% of the world's energy, even though it only has 4% of the world's population, right? So Americans use roughly 4 times as much energy per person as the world average. We can just say use 4 times as much energy. We don't have to say usage. Per person as the world average. Okay, you can try the next one on your own. That's kind of a fun one to do. And you can use the table to figure that out. Okay, let's look at the last one. Here, human civilization, at least since the time of ancient Egypt, is on order of 5,000 years old. The age of Earth is on the order of 5 billion years old. Suppose we use the length of a football field, or about 100 meters, as a timeline to represent the age of Earth. If we put the birth of Earth at the start of the timeline, how far from the line's end would human civilization begin? And if you need to pause the video and reread the problem, please feel free to do that. So the first thing I'm going to do is I need to take the age of the Earth, and I'm going to compare that to the human civilization age, right? So what part of the age of the Earth is the human civilization age? So I've got 5,000 years for human civilization compared to 5 billion years for Earth. Well, 5,000 can be written as 5 times 10 to the third years. And 5 billion, remember, is 5 times 10, and then there's 9 zeros. So I know the years cancel. I know that the 5s are going to cancel. And again, when you're dividing like bases, you just subtract the exponent. So 10 to the third divided by 10 to the ninth is really just 10 to the 3 minus 9, or 10 to the negative sixth. Okay, what does that mean? Well, 10 to the negative sixth is a 1 with 1, 2, 3, 4, 5, 6, with 1, 2, 3, 4, 5 zeros before it. So here you have tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So 5,000 years is about 10 to the negative sixth, or 1 millionth the age of the earth, which is kind of hard to think about, right? Now, if we're comparing that to a football field, which is 100 meters, then that means we need to take 1 millionth of 100 meters. So 1 millionth, again, is 10 to the negative sixth. And then of means multiply. 100 is 10 to the second power. So now when you are multiplying like bases, we add the exponents. And you get 10 to the negative fourth power, right? And what does that mean? Well, again, this is in meters, okay? So let's put it in terms of something we can think about. 10 to the negative fourth, let's change it to millimeters, right? So we can think about, size there. Millimeters a lot smaller than a meter. So all I'm going to do is I'm going to convert now. I've got 10 to the negative fourth meters, okay? And how many millimeters are in a meter? Well, there's 1,000 millimeters, or 10 to the third millimeters, in 1 meter. So now I can cancel them out. And again, you're multiplying like bases, so we add the exponents, and you get 10 to the negative first, or 1/10, 0.1 millimeters. So think about how small that is, right? What does 0.1 millimeter look like? Well, a millimeter is extremely small. So 0.1 millimeters is 1/10 of that size. And if you think about that 100 meter yard line, right? The length of the football field, the age of the human civilization is only 1/10 of a millimeter of that. The Earth's been around for a long, long time. So that kind of puts it in perspective when we do things like that, and we compare things. You could have left your answer as 10 to the negative fourth meters, but it's a lot harder to think about that. It's much easier to think in terms of millimeters here because it's so tiny. And it really puts into perspective how long humans have been around compared to the actual age of the Earth. And that's the end of the video. I hope you learned a lot. So if you have any questions, please feel free to reach out to me.